Hello, in this video we'll move into section 13 where we will discuss rational functions. As you've seen in section 12, we're in that point where we kind of need factoring for so many of our problems, and that's going to continue into this section as well. What do we mean by a rational function? Well, a rational function is defined simply as a polynomial over another polynomial. So we spent all our time working with polynomials, and now when we see these rational functions, our book suggests that when we hear the word rational in math, we should think of fractions. We're getting this type of fractional setup. So as a function, reminder of our function notation, I'll use an f of x here. We might be looking at something like x squared minus 2x plus 5 over 3x minus 4. Or something like g of x is 3x minus 1 over x squared minus 4. Things like this. This is what we're talking about. A polynomial over another polynomial, same thing here. For those of you who go into pre-calculus, you'll eventually learn more things that get into what facts regarding the highest exponent on top and bottom, numerator and denominator. But for us, just to establish, that's what we're talking about. There's nothing better or special when the higher exponent is on top versus the bottom. So first thing, now that we're getting back to our function notation, just a reminder about how this works, something like, let's evaluate, and let's start off with f of 1. Let's find the value for f of 1. Well, it's been a little while since we've done our notation, but the idea, we've seen this in a graph, we've seen it with equations. With a graph, I've given you the x, you're looking for a y, and that's the same thing with the equation, except how do we find that y? We plug it in. Wherever there's an x, I replace it with a 1. I'll get a 1 squared minus a 2 times 1 plus 5 all over 3 times 1 minus 4. Now I'd go through and do my arithmetic. Order of operations, I'm looking across the top. 1 squared is 1. Minus 2 times 1 is minus 2 plus 5. The bottom 3 times 1 is 3. Minus 4 stays. And now I've got my addition subtraction. 1 minus 2 is minus 1. Plus 5 is 4, positive 4. 3 minus 4 is negative 1. And finally, 4 divided by negative 1 is negative 4. So f of 1 equals negative 4. If we were graphing this function, that would be an xy pair that we could put together. But we're not going to be graphing here, everybody. We're getting an introduction to these functions. We're seeing a little bit of the function notation. But what we are going to go back to next is the domain. And once again, that's something we have seen before. The idea of domain, we're talking about the x values. But up until this point, we have just actually looked at the graph and said, oh, well, I go from here to here. Those x's use our interval notation. Now we need to realize there's a little bit more going on here. The fact that when I plug an x value in, the fact that I ended up with this fraction in the first place, I ended up with division at the end of the problem. There's a potential problem here. Let's go to the second one and see it. I ask you to find g of 2. So the g, that's pointing me to use this equation, not this one. G of 2, I gave you x is 2. And initially it doesn't seem so bad. I start plugging in 3 times 2 minus 1. The denominator, 2 squared minus 4. I start doing some arithmetic. On top, I get 6. 3 times 2 is 6. 6 minus 1 is 5. But look at the bottom. 2 squared is 4. 4 minus 4 is 0. We ended up with 5 divided by 0. And again, remember, folks, the other way, if it was 0 divided by 5, that's no big deal. That's 0. But 5 divided by 0, that does not exist. You can't divide by 0. 0 times what gets you to 5? Nothing. Versus here, 5 times what gets you to 0? 5 times 0 gets you to 0. So it's been a while, but we saw this with slope, that we saw vertical lines, slopes ended up looking like this, that led to an undefined slope, versus horizontal lines, slope ended up like this, we ended up with a slope of 0. So these are two very different things, but the point, this can't happen. So when we talk about the domain, we talk about what are the x's we can use, and right now we're seeing an x that we cannot use. So the point for domain, for a lot of functions when we look at the equation, we think about what can't happen, and that helps guide us to what can happen. So back to both of these, let's find the domain of each. Start over here, I'm looking for trouble. When I have a fraction, what's trouble? Well, I can't divide by 0. So when I'm trying to find the domain of function f of x, I'm looking for its trouble spot. Its trouble comes from the denominator. The numerator, I don't care what I get in the numerator. Any of these situations, having a whatever on top is fine. The problem is I can't have this 0 in the denominator. So what I do, I set the denominator equal to 0. I solve and I find the trouble spot. And in this particular one, you just use my pen to separate these problems a little bit here. So now I'm solving this equation. It's a basic equation. Only x to the first power, so I'll isolate my x. I'll add a 4 on both sides. Here the 3x comes down. Over here, 0 plus 4 is 4. I'll divide both sides by 3. And my solution is x equals 4/3. But the point here, that's what I want to throw out. That's the x that makes this expression equal to 0. That's the x that does something like this. So that's the x we need to get rid of. So what I'll do, I'll think of my number line, and this is the x I'm getting rid of. So I'll mark it off. I'm getting rid of it. I'll leave it as an open circle, and I'll take every other x. So I'll take all the x's that came in front of it. I'll take all the x's that came after it. And if we remember for domain, we almost expect to use interval notation because we're going to get stuff like this. In this particular case, I got 2 intervals. This interval here, everything that came in front of 4/3, forever to the left, that would be negative infinity, up to this point 4/3, but not including it, so a parenthesis. And then I'll get this interval over here, starting just past 4/3. So starting at 4/3, but again, not including it, so parenthesis. And now this goes forever to the right, so goes to positive infinity. Both of these are my answer. As we've seen in some other situations, when you have 2 intervals, proper notation, you can use a union symbol, but I'm perfectly happy if you just have the 2 intervals. Okay, let's do that again. In the next problem, we'll come over here and we'll look at G. Let's find the domain of G of x is the 3x minus 1 over x squared minus 4. And in that same way, the numerator doesn't matter. The domain is about the denominator in this problem. That's where I can get potential trouble. So I'd set that denominator equal to 0. I'll solve. Now my equation is a little bit more complicated. I've got a square here, so I'll factor. It's already set equal to 0. That's a nice little bonus. I'll jump into my factoring. This one should have pointed out, right? I don't see any GCF. I see a nice binomial, and I see it is in the form a squared minus b squared. So I factored a minus b times a plus b. Now I'll set each factor equal to 0. Over here, add 2 on both sides. I get x is 2. Over here, subtract 2 from both sides. I'll get x is negative 2. Now, we've already seen this one. I already used 2 and saw I was in trouble, so not too big of a surprise, but starting as a fresh problem, big picture is now I see 2 trouble spots. 2 different values for x that make that denominator 0, so 2 values that need to be thrown out. So just like I did over here, I'll go to my number line, I'll show what I'm throwing out, so I could shade in everything that I still want to keep. Now, just be careful here, folks. You're doing a number line. Make sure you put these in order. There was only one value here. I didn't have to go nuts. I just had to mark it off. But here with the 2 values, make sure they're in the right order. Negative 2 would be over here. Positive 2 would be over here. I'm throwing them both out. So I would have everything in front of negative 2, everything between negative 2 and positive 2, and then everything past positive 2. This time I see 3 intervals. This one, forever to the left, that's starting at negative infinity, and it finishes at negative 2, not including it. Then I'm starting at negative 2, not including it, going up to positive 2, and then starting at 2, not including it, going to positive infinity. All parentheses here, that is the domain of function g. So a nice little start with domain, and for some students, it's been a while since they've seen domain, so to make some of those connections, remembering how it connects to x, and remembering just bigger picture, our form, we want our interval notation, so it feels a little different, but really, in reality, it's very similar to what we were doing when we first introduced domain, just having an equation to figuring out trouble spots and seeing a good interval as opposed to the graph. So nice start, but now we very quickly want to move along and start talking about simplifying these rational expressions. For simplifying, it's very simple. Like our regular fractions, if I have something like 4 over 8, I can reduce that. I could see I have a common factor. I know 8 is 2 times 4, so I could cross off those 4s, and I'd be left with 1 over 2. It's the same idea with rational expressions, with these rational functions. I want to think about the factors of the top and bottom, and I want to cancel the common factors. So let's jump right into a problem. Let's simplify 2x cubed plus 10x squared over 4x squared minus 4x. How are we going to do that? Well, up here with numbers, some of us already have quicker instincts, but it's the same idea. The key to make this cancellation is, again, you're canceling a common factor from top and bottom. So the key, I'm going to need to factor these expressions. And this is where our book makes a very good point. Some people just see, oh, you cancel common stuff, and they start jumping all over. They're like, hey, I've got an x squared here that crosses off with this x squared. No, it doesn't, everybody. It needs to be connected by multiplication. These have addition-subtraction connections. So again, hence, just like when we're solving an equation in a complicated situation, I need to be able to multiply these to set each multiplier equal to 0. Well, now I need to break this apart by its common multipliers, its factors, so I could look top and bottom to cancel those common ones. So in this first one, well, factoring. I look at the top, I see a GCF. I see 2 and 10 share a common 2. X cubed and x squared have a common x squared. 2x squared is coming out. What's left behind? Keep saying it. Do you need to divide it out? 2x cubed divided by 2x squared to see what's left? Can you just think of what came out, so what's left behind? Whatever way, you got to have an ability to see what's left behind here. And in this case, here it's an x, and then here it's a 5. 2 came out, left a 5, both x's came out. In the denominator, well, 4x squared minus 4x, I see a common 4, and I see a common x. 4x came out, x left here, 4x came out, 1, specifically a minus 1, left here. Now I'm looking top and bottom. What do we have in common? What are the factors that can cancel? And now in here, things, expressions, factors like this, they've got to be perfect. They've got to be identical. It's what we were saying earlier. I can't just like, oh, they've got an x and an x, cross that off, and I'm left with a 5 over negative 1. That's garbage. That's just like over here, crossing off these x squareds. So these are fine, but over here, now individually, because this is all multiplication, I can work on the 2 and the 4 like I did the 4 and the 8. And that a 2 cancels and a 2 is left here. And then I could work on the x's. This is just like when we did our regular exponent section, everybody. This division right here, I'm doing what's nice. The number with the number, the x with the x. 1x will cancel. So I've got 1x here, this x canceled. What's left? Well, this x is still left. This x plus 5 is left. And in the denominator, this 2 is left. And the x minus 1 is left. And in these problems, folks, we'd like to just leave it factored like this. There's no good reason to redistribute. I needed to factor it so I could see what cancels, but now that I have canceled, nothing wrong at all, and actually it's just kind of a better habit to just leave it, whatever's left, in its factored form. Okay, let's do another one like that. We're still simplifying. This next one, let's look at 25x minus 5x squared over x squared minus 25. There's a lot of common stuff around here. But again, at this moment, nothing cancels. I can't just pick and choose, oh, 25s and x squareds, and that is an x. It's not perfect right now. The addition, subtraction between these would have to be identical, and they are not. So once again, I start looking for the top one. I see a GCF. I see a 5x that comes out. So a 5 would be left here, minus, and an x will be left here. The denominator, the x squared minus 25, I don't see a GCF, but I see an a squared minus b squared, so that'll factor a minus b times a plus b. And just as I said earlier up here about GCF and doing what you need to do to have the right leftover pieces, do you need to divide? If you do need to divide, can you do it in your head? Should you do a little work off on the side? That's all up to you, but same thing here. I use difference of squares. Do you need to write it out to see a little more? Do a little work on the side, then bring it back together? You do what you need to, but this needs to be cleaned together for us to see what happens next. And in this exact moment, there's a lot of similar stuff, but nothing's perfect. I see similar stuff, but 5x and x plus 5, that's not the same. These are really close, but they're backwards. And this is where our book loves stuff like this. So close, we got to realize we can actually maneuver to make these perfect. That 5 minus x is really the same thing as minus x plus 5. And minus x plus 5, if I take a negative out of it, I'd be left with a positive x here, and I'd be left with a minus 5 here, and now those cancel. So that for some people is a little weird, and just to realize now what's left, the minus and the 5x are left on top, so a minus 5x, and the x plus 5 is left on the bottom. But come back to the beginning. That's a little goofy for some people, and right off the bat, this felt weird partially because we've kind of established a tradition. We like our polynomials to go from highest exponent to smallest. This was out of order. So just a little adjustment some people like to make for that, put it in order. Make it minus 5x squared plus 25x instead. And now when you go to do your GCF, we've seen that before. If my leading term is negative, when I do my GCF, I'll take the negative out with it. So I'll take a negative 5x out. And now I'd be left with a plain x here and a minus 5 here. And I'd see the x minus 5's immediately canceling, left with the minus 5x over the x plus 5. Okay, so we're off to a good start here, but we're still just getting started. The domain, a nice introduction, reminder of functions, connections to x, simplifying to see how we simplify fractions like this and how similar it is to what we used to do with just numbers. In part 2, we'll get into the multiplying, dividing, addition, and subtraction.